Let's get going on day 4. Today we're going to talk about linked lists. Hope you guys had a good weekend. So we made it through a first full week of Comp 15. We've done a lab. I hope that went all right. We had an assignment due. We'll do a little debrief on that in a few minutes. And we've done some lectures and things. So I think I forgot to mention this on the first day of class. There is an anonymous feedback method that I've set up. If you go to I think it's either the syllabus or the first page of the website, and you go down there and click. It's called say at.me or something like that, and then /Chris Gregg. I think that's what it is. You have to look specifically. But if you go to that website and you want to give me anonymous feedback, in other words, you don't want to email me for whatever reason. The class today was terrible. You thought the homework assignment was rotten, blah, 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 and you don't want to actually let me know who you are. You can tell me this anonymously, right? And I can actually respond to you anonymously as well. I would rather whatever anonymous feedback you give me is somewhat constructive, right? I mean, if you want to say, hey, that assignment was terrible, you suck, fine. But I'm probably not going to reply, right? I mean, if you say, look, the assignment was bad, and here's what could have been better, awesome, right? I'm totally up for that. And you can be anonymous, and that doesn't bother me so much. Obviously, you can email me as well. So I think I forgot to do that. But now would probably be a good chance if you think something's drastically wrong to give me feedback already, okay? I will try to make changes if it's constructive and good feedback. Yes?
You said you could respond anonymously. Are there other people who could be responding to us?
No. So I get an email that says, no, it's not me being anonymous. You stay anonymous to me, in other words. That's all. No. It's not. That would be kind of funny. Some random dudes replying. No, someone's replying. No. No, you stay anonymous. We can have a dialogue when you remain anonymous. That's all. OK, so here's what I'd like to do today. Let's talk about homework 1. Just do a quick debrief on that. And then we'll do the Unix tip of the day, Eclipse tip of the day. We will do a little bit of just a quick recap, because I didn't quite get to the last slide or two on asymptotic analysis from the other day. We are going to start using it today when we talk about linked lists. So you'll start to get a feel for how we actually apply this to real data structures outside of an array, which is kind of what we did the other day. And then we'll actually go into linked lists. Now, most of you guys have probably programmed linked lists before. I'm almost 100% certain you did in Comp 11, right? And last semester when I taught this, I made the mistake of thinking, oh, you did it in Comp 11. That means you understand it. Right? And unfortunately, you may have understood it at that point, and that's awesome. You may have forgotten some of that. But linked lists are not particularly hard. They just take a lot of thinking to make them to get it right. It's one of those things where if you're really good at attention to detail, linked lists are fine, right? But if you're kind of like me and you're I'm not very good at attention to detail, and this looks right, you're going to miss all the corner cases that are associated with linked lists, right? So we will go through some of those in here. And your homework 2, which I still have to post, I'll do it this evening, is actually virtually identical to homework 1, except now you're doing all the data structures as a linked list, right? All the insert before, insert after, remove at, all that kind of stuff. Oh, and I'm getting oh no, couldn't be. It's not that bad. It's just kind of another level of attention to detail in that sense, okay? And obviously you have to understand this. Linked lists are particularly important. It's particularly important with linked lists than any real link-based structure to draw out what needs to change if you're making modifications to the structure. Okay, I mean, if you either have a mental map of it or actually put boxes on paper to figure it out, because that makes it completely transparent about what you're trying to do. We will get into all that. Okay, then we'll talk about doubly linked lists, which happens to be what the lab is all about. Today and tomorrow. So hopefully you at least glanced at the pre-lab. Those of you who do the lab right after this class, or I guess the first lab is at 4:30 maybe, you've still got some time, but I know it's not that much time to process all this, but if you pay attention today and then do the pre-lab, you should be all set for this week's lab. Okay? All right. Any questions before we launch into here at this point? No? Okay. Homework 1. I haven't looked at it yet. Over the next week, the TAs and I are going to sit down, and we've got this you've already seen some of the auto grading, but we've got this kind of online grading thing where we take a look at your code and we see how you performed on the tests, and we check the code to make sure it's indented properly and all that kind of stuff. And then we give you a grade, and it takes a while for everybody to do that. So hopefully I'll have the results back by, let's say, next Monday. Yes?
In the README files that we had to include the homeworks,
yes.
The thing is, like, most of the stuff we were doing was just simple dynamic array stuff.
Yeah.
And do our algorithm segment have to be like super intense?
No, your algorithm section did not have to be super intense. Not for this one. There's other ones where it will be. You'll have to do more explaining. When we get to an assignment on building your own sorting algorithm, if you want to build your own, you have to explain it. Like there's like going to be more to do with that. This homework assignment, all of those nice comments I gave you, I'm not going to give you this time. Right? I'm not going to give you your own comments. In fact, I'm going to give you the .h file and then a very truncated .cpp file for the linked list. You're going to have to do a lot of the figuring out on your own about how to do some of that. So there will be more commenting and kind of explaining in this one. Not too much more explaining, but enough. Yeah, good. Question?
When will homework be due?
It's due a week from Friday. Another week, 2 weeks, almost 2 weeks. Yeah. Week from Friday. On that note, so first of all, congratulations. I got very few people saying I didn't finish for X, Y, and Z reasons. And if you did, that's fine. But that means that either you guys are scared and don't want to tell me you couldn't finish the assignment, or you did great on it, or you just for whatever had some other crazy reason. But if, in general, I'm very, very happy when I don't get that many people saying, oh, I need an extension. It means the assignment was probably about the right kind of hardness in that sense, or too easy, which is something else it certainly could have been. Does anybody have any comments on easy, just right, or too hard for that assignment, homework 1? Just curious. A couple people going, yeah, it's all right. A couple people saying, could have been easier, but any assignment could have been easier. Anybody think it was way beyond what just give me the old wink. If you think it was too hard, I'll look around. No, I'm not seeing too many winks. OK, so I haven't seen any winks. No winks. I think in that sense, I think it was probably about right. This next one, same idea, will be probably half an order of magnitude harder because linked lists in general take more work to get right. The other thing is we haven't looked and seen if you guys did extra stuff. Feel free to expand on if you wrote a little card game or you did something, expand on it if you want. If this assignment also is relatively easy, go for it. OK, I'm perfectly willing to have you do that, or just do the assignment and do fine on it. OK. Any other comments on homework 1? No? OK. All right. Then I will put that to bed until we get the results back. OK, the Unix tip of the day. So this one, a couple people emailed me frantically and said, hey, my files disappeared. Oh my gosh, Eclipse deleted my files, and that I don't think that happened. I don't think Eclipse deleted anybody's files, but some people lost their, didn't find or their files got deleted. Well, turns out that the CS department keeps backups of your stuff. Now, it's not instant backups. If you have a file and then 10 minutes later you delete it, you probably don't have a backup. But if it's a couple hours later and you're coming back to a file and all of a sudden something goes wrong, the odds are very good that we have a backup somewhere. It's in the .snapshot folder in your main directory. Okay, so let me show you what this looks like. Okay, let me make sure this is the right size. Hang on. There we go. OK. If you do cd.snapshot from your main folder, it's a hidden file, right? And you look in there, you do an ls in there, it says hourly.0, hourly.1, hourly.2, et cetera, and then nightly 0, nightly 1, nightly 2, and then weekly 1, weekly 2, which means that it's keeping backups roughly at these time spans, OK? Now, it doesn't mean that within the last hour there's necessarily been a backup, but hourly 0 is a couple hours old at the most, OK? And if you go into, let's say we go into hourly.0 and then do an ls in there, there's all my files, right? And they're all modified a couple hours ago or more. And if I deleted something, it would be in there. So watch this. Although this isn't gonna be that impressive, but let's say I do remove readme.txt.bak, right? Well, it's not in my main folder. if I go to .snapshot, if I can spell, .snapshot and then hourly.0 ls, well, readme.txt.back is obviously still there. So I only deleted like kind of the main copy, and these are the backups. So you have some good backup ability in there. Yeah?
How would you be able to bring that back?
So what I would do is I would say, oh, phew, I found my file. And then I would go cp readme.txt.bak to my home folder, which is the tilde, or wherever it is, right? Just copy it back in there. Okay? You can't write to this directory. I don't believe you have the ability, to write to your own. You might actually. I'm not sure. In general, you can't. You're not supposed to be able to write to your own. To write into your own snapshot, but you might be able to. If you wanted to do some sort of like horrible delete of all your stuff, you probably could. Yeah.
Do all the files move throughout the? So there's like hourly.0, 1, 2, 3.
Yes.
So like at each iteration, does 0 go to 1?
Yeah. It bumps to the next one. So hourly 1 was hourly 0 2 hours ago, or whatever, something like that. Yeah. Okay. Questions on that? That hopefully will save some of your assignments at some point. Well, hopefully it won't. You won't delete anything. But if it does, you don't worry. There is probably a backup if you're keeping your files on the system here. Okay. All right. Did you guys ever see there was something that went around the internet? It was a little poster somebody had posted outside the apartment building, and it said outside their apartment building, and it said, "If you stole my laptop, I will give you a $5,000 no questions asked reward for returning it, because my entire dissertation, which I've been working for 5 years on, is on that laptop, and that is the only copy I have." And I have no idea if that person ever got it back. But bad news, people. Dropbox is your friend, right? Don't do that. You should have seen all the backup copies. I would like routinely, with my PhD dissertation, I would like routinely email it to myself, my parents, my sister. I'd be like, look, you don't just print this out and just keep it in a box, right? That was it. So, no, Dropbox and those other companies are pretty good about spreading your data out far enough around that an earthquake in one part of the country doesn't destroy your data in the other part of the country. So it's actually an interesting problem, keeping your data distributed enough, secure enough, and also able to be found when you need it in a pinch. But Dropbox, Google, all those places do that. It's cool. All right, questions on snapshots? No? Okay. The Eclipse tip of the day is not so much, what happened here? I don't know why I did that. Nope, there it is. The Eclipse tip of the day is not so much about Eclipse, but a lot of you guys are still getting these core and Java core and snap files, which is what Eclipse puts in your folder. And if you're running out of disk space, this is what you want to do. Now, some of you guys actually have lots and lots of core files from Comp 11. Because lots of seg faults happen in some projects. I think the fish one was a big one I saw where people you guys know you got lots of like seg faults in that, right? Well, here's a little set of commands, okay, that if you run, and make sure you either copy them and paste them or run them exactly, because whenever you use rm, you can sometimes get in trouble with deleting too much. But in this case, if you write this exactly the way it is up here, bash and then for f in core, blah, 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 this will delete all the files called those in your directory system, especially if you run it from your main system. So it will clean out a lot of those things. The core ones in particular are the big ones. If you happen to name a file core, I don't know, comp 15 stuff, well, then it deletes that too. So be careful there. Right? Make sure that if you ever named anything core or something, that you go back that up. All right? Question?
So is this just a script writer? Can you just write these commands in?
You can actually write these commands in. What will happen is here, let me show you. Well, it's probably easiest to do it. Let me show you. So if you write bash, I actually run bash as my I don't know why I'm blanking on the word, as my terminal emulator or my shell program. And you guys may not. You might have some other, but bash gets you into this nice mode where you can do all these commands, right? And then if you do for f in core, let me see, Java core snap, and then semicolon do, it will actually give you a little caret and saying, hey, I'm waiting for more stuff, right? And then it will, let's see, and then find dot dash name dot $F is the variable we just named. This is bash scripting language. It's another programming language. Slash, actually, I goofed already. Should be F/* like that. That probably would have been bad otherwise. Actually, that would have been really bad. Now that I think about it, if I had left the space in there, that would have like deleted, it probably would have deleted everything. So, and then I would have gone to my .snapshot and had egg on my face. But anyway, be careful when you do these. All right, let's see. Dash exec rm. Yeah. Maybe I should write this into a script so you don't have to type it. It'd probably be easier. All right, and then done. And then it should go through and find all those. And it sometimes takes a while. I'm not going to actually let it continue. If you have a lot of files, it'll look through a lot of files. I didn't just delete everything. Nope. OK. And then exit gets you back out into your main shell. So you can just type them right in there. Answer your question. Long story for that answer. OK, question?
Do you have to type that command in a folder or like a directory where there would be those files?
Yeah, you can actually start off if you type CD beforehand and then enter. It will take you to your main folder. Or you can do it from within the folder. Doesn't matter. If you do it from the main folder, again, if you type it wrong, you could end up deleting all your files, which you would want to copy back. If you did that, first of all, you should yell at me for even giving you this tool. But then second, you should probably see somebody about making sure we get this stuff back for your .snapshot file. Yeah?
If you wrote it in the script, how would you execute it?
Good question. Let me show you. You would first of all start out the top. You wouldn't need this bash like this. You would need, let's see, hash. This is called a shebang. It's called a shebang because hash exclamation point. Bang is like exclamation point because when you say something exclamation point, it's not bang. Anyway, and what you would do is you would do something like /usr. I'm trying to remember. Hang on. Which? Oops. Let's see. Which bash? /bin/bash. So it would be like this. You would type /bin/bash. And that says, hey, use bash to run this script. And then you would save it, and you would have to change the permissions to be executable. And then you would run it. And then you would just do // whatever the name of the script is. Okay? Or you could type sh and then the name of the script too. But that's it. OK, other questions on that? If you need to delete things, you can be daring and do that. Oops, forgot bash. All right. All right. Question?
No way to tell it to take a snapshot right before you do it? So that way
There's no way to take a snapshot right before you do it. So yeah, wait a couple hours before swimming. No, go wait. You could wait and then do it after you haven't changed any files, I guess. But don't let it scare you. It's just there is a backup, so that's not the end of the world. OK. Asymptotic behavior summary. So we ended here the other day, and I just wanted to go back and kind of do just a run through of the different types of asymptotic behavior we will have to know for class. OK? Constant behavior. Constant behavior is the holy grail. It's the one we always would love to get. It basically means I don't care how much data you have, whatever operation you're trying to do, you can do it in what we call one operation. You can do it instantly. Okay? You do not have to go through and loop through all the elements. You don't have to find elements. You just do it, right? Then the hash table that we'll see in a couple months is a prime example of constant behavior, okay? And it just does not depend on the total amount of data. All right? Linear behavior. Now, this is the one where if you add 1,000 more elements, right, well, 1,000 times as many elements, you will take roughly 1,000 times more time. Right? That's linear behavior. Okay? If I have 10 times as big a list, I'm going to take 10 times as much to do it. Here's why. At each step, you're only reducing whatever problem you're trying to solve by a constant amount, like 1. Right? You go for I equals 0 to n, right? And each time you go through that loop, it reduces the problem by a size of 1. Right? You guys have all sung 99 bottles of beer on the wall, right? Maybe you haven't. 99 bottles of Coke on the wall. Anyway, this is on video now. Anyway, that's reducing the problem by 1. You know why it takes that long to do that? Anybody ever gotten through that whole song? I've never gotten through that song. Get to like 87, and you're like, forget it. And the bus driver's about to drive off the road anyway. So linear. Add 10 times as much, 10 times as much time. Okay, we try to avoid linear if we can help it, but sometimes you can't. And it's not too slow. It's just not the best. Logarithmic is this one where you're cutting the problem into half, 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 or a third, a third, a third, a third each time. And we love logarithmic algorithms, right? Because you can get through the log of 1024 is 10. The log base 2 of 1024 is 10, which means you can take a problem that's 1024 and break it into 10 steps, right? Which is great. And you double it, and it's only 11 steps, right? So logarithmic behavior is great, okay? Binary searching is the one logarithmic behavior we've kind of seen so far. Okay, when we talk about trees, we will get into lots of logarithmic behavior. All right. Quadratic behavior, this is the one where it's doubly nested. You've got two for loops, one for loop inside another for loop, and it's kind of slow, and it grows like this. It's very slow. 10 times more elements is how much slower? 100 times, because it's 10 squared, right? So not so good if you can help it. And we do deal with quadratic algorithms a lot when you're dealing with displays and pixels and things in a two-dimensional grid. Well, you're going to have to do quadratic type data. Again, this is why your GPU has been specifically engineered to speed up graphical displays, because of this problem, this quadratic issue. Okay, cubic, same idea, just add another dimension, even slower. Not so great. Okay, triply nested things. And of course, the world is three-dimensional, so there you go, triply nested. And then exponential, this is the one where you're reducing a problem, and I might not have stated it this way before. You're reducing a problem into two or more sub-problems that are smaller. So it's not that you're just breaking the problem down into smaller problems, right? You're breaking the problem down, like you're not breaking it in half, 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 or whatever. You are reducing the size of the problem. Like you will eventually finish the problem. But each one of those, like you're breaking it into other sub-problems, and each sub-problem breaks it into more sub-problems. So there's this kind of expansion of work you have to do. And so exponential is not so good. This is the heat death of the universe one, right? If you're doing exponential problems. It's like that the Tower of Hanoi that I showed you. Once you get past about 8, it's just going to explode in amount of time. Okay? All right, questions on that? These are the ones we're going to have to look at. These are the ones that we will talk about for every algorithm we do for the rest of the class. Okay? Awesome. All right. Let's get into the meat of this stuff. Linked list. Like I said, you guys have most of you have seen linked lists in some form or another. It's taught in lots of classes. I will tell you right up front, you will rarely want to actually use linked lists in real life because they're kind of slow for a lot of reasons. But they are a good example of a linked data structure, and they're the kind of the easiest example of a linked data structure. So that's why we actually tell you how to write them. Okay. In the notes at the end of this presentation on the slides, there's a video you can link to the creator of C++. His name is Bjarne Stroustrup, and he wrote the language you guys all hate. And but he's actually a really smart dude. And he specifically during this 7-minute video says, don't ever use a linked list. Right? Because they're kind of slow, and there's reasons to use other data structures instead of linked lists, and any benefit you get from linked lists are probably going to be outweighed by the deficits you have to use. But regardless, all that good news, let's learn what they are. So linked lists are based on these ideas of a node, right? And we almost always draw a node as just a box, and these boxes, just like on the screen here, these boxes have information in them. They have like data in them, right? And then each link has an ability to say, hey, here's the next link, or the next node rather, right? So you've got nodes that link to each other. I mean, that's why they call it a linked list, right? And in C++, the link is actually a pointer. Okay, I'm going to show you in a second what that like looks like in C++. But the link itself is a pointer that says, hey, this is where you go to find the next link. What that means is that instead of having a nice array-based system here where you've got a bunch of boxes in a row, you can have a node in the first part of the memory, right? And it can point to a node somewhere else in memory, which can point back to some other node in an earlier place in memory, like this. So it gets fragmented. like this. Okay, and the memory is not particularly well set up for linked lists. Okay, there are benefits to this model, which we'll talk about in a couple minutes, but this is not like, from a memory standpoint, memory systems don't really like linked lists for a lot of reasons. Anybody have any idea what this model breaks in terms of a lower level computer architectural reason? Alex, what do you think?
Well, the works can get gummed up really easily because if all the different things are stored out of order, then you're going to have to do a lot of, searching and digging around and going from pointer to pointer to find.
You do have to go from pointer to pointer. Yes, that's a very good point. I was thinking even lower level than that. Yeah.
On a hard drive, data is arranged in linear sectors.
Yeah, on a hard drive, this is great. Have you ever had to defrag your, you guys don't really have to do that often anymore, but you defrag your hard drive, that's because it gets fragmented, where a piece is here, then a piece is here, and a piece is here. Before we had SSDs, hard drives took time to literally find the next piece of, say, a linked data structure, because you have to like physically move a read head. Okay, so that's a good example, right? Go ahead.
Memory, you can read a whole address of memory at once, and so then you have to, if you're jumping around, then you have to go back and you might have to reread that memory again if it's in the same kind of block or something like that.
Exactly. So that's exactly right. So if you didn't hear him, he said, what's your name?
Logan?
Logan said, the way the memory system works, you can actually read a whole block into memory at once. And what you're actually getting at is this idea of caching data. Okay, and you may not have heard this before, but C-A-C-H-E. If you cache data, it means that you put some data in a much faster location in memory. So your computer actually has a whole bunch of, you go and you buy a computer and it's got 8 gigabytes of RAM, right? That's one part of your memory. Under the hood, there's also a number of levels of what we call cache memory, which you can also look at the fine print and it says, oh, it's got a 4 megabyte L2 cache and a 1 megabyte L1 cache and all that. What that is, that's actually faster memory, right? So you've got this kind of hierarchy of memory. And what you can do is copy a whole block from slow memory, that 8 gigabytes, which is fast, but it's slow in a bigger picture. Copy that into the fast memory, and then use the pieces as you go. And as Logan was saying, let's say that this first box was one piece of memory, and then there's another box over here, which is the next piece. And some of these links this link pointed to something in the other box. You would have to read this in. You'd get some of the data, and then you'd have to read this one in when you got to this piece of data. And then if you wanted to go to the next link, maybe you'd have to go back here and read in this one again, and it wastes time. So there's these ideas where if your memory gets fragmented, you're going to break all this amazing caching ability that hardware engineers have been spending 30 years perfecting, right? So this is kind of one of the reasons that it's not so great to use these fragmented data structures. But that said, there are other reasons to use them, and and we'll see some of those. Okay? All right, so a linked list, this is slide 7, a linked list always has a starting place, right? And the starting place is called the head of the list. Okay? The head is a pointer to the first node. It's not the first node. Now you can say, oh, the head node. Okay, you're kind of mixing it a little bit, right? The head of the list is a pointer which points to that first node and always points to the first node. Okay, we just call it the head. It's a pointer just like any other pointer, and it points to the first node. And that's how we find the beginning of the list. If you lose the head of your linked list, you're done, right? And some of you will actually write your program, probably even for the lab today, where you accidentally overwrite the head before you figure out what's next, and you're done, right? And the whole rest of the linked list is gone, okay? Because that shows you where it starts, okay? All right. Sometimes, not always, we have a defined tail to the linked list as well. A tail's a nice thing to have because it says that's where the end is, right? The tail points to the last node, obviously, right? It's the tail and the head. So in Comp 11, at least a couple years ago, Professor Sheldon was saying that anything that's not the head is part of the tail. Is he still doing that? Yeah, we were trying to tell him not to do that, but we don't like that because in this case we can call the tail the last node. And for our purposes, if you have the tail, it's the last node. Not everything but the head, it's just the last one. Okay? You might see it defined differently. Professor Sheldon, I guess, defines differently. But in our cases, the tail is the last node. Ben?
Yeah. So in coding terms, you would still say head equals whatever the last node.
In coding, right. If the head at this point is pointing to the first node, if you say a new node equals the head, that will set the pointer of the new node, or sorry, the head equals the new node. That will set the head to point to that new node. That's how you do it.
Also,
Yeah.
Does the node have a name, or does it just point to the value inside the node, or the value?
It points to the structure of whatever that node is, and I'll show you that in a minute. But yeah, good question. Yep.
So if the head is a pointer to the first node,
Mm-hmm.
is the tail the pointer to the last node, or is it the pointer contained in the last node?
No, it is a pointer to the last node.
Okay, and then
Yep. It's not the, notice, so here's the last node, and the last node has a little next, and right now this is pointing out into nowhere land, right? The tail points to this last node. That's that. Yep.
So the node is structural type.
It's a, yeah, you'll see in one sec. We're going to define it as a struct, as you'll see in a sec. Yep, Mariah?
If you wanted to get rid of either the first or the last node, could you just move those pointers, or would you have to actually delete that node and then move the pointers?
Very good question. The question is, if you want to get rid of one of either the tail or the head, can you just move the head? Yes and no. If we said the head now points to this node, well, now the list would be from here on out, the second node all the way down, right? However, this one's just hanging out in memory, and that's called a memory leak, right? So you have to handle this first. You would say, yep, the head points here, but first I'm going to delete the node. I'm going to delete the head, and then I'm going to move the head pointer to point to the new node.
Is the syntax for deleting similar to the
It's the same. Yeah, if you're deleting a struct, it's the same. Yep, exactly. Yep.
So, unlike, say, the Comp11 implementation of linked lists, we're sometimes going to have pointers that point directly to our last element that aren't contained inside other nodes. Like we're gonna have,
Yes. Yes, you will. You will have a tail that points to the last one in this case. Yep. And that's only sometimes. It depends on how you build it. Yep. And we'll talk about how that's good and why that's a good thing. It does mean more bookkeeping, but that's good. Good. Other questions about this? All right. So the tail of the linked list always points to the tail of a linked list. In other words, the last node in a linked list, I probably should have said this differently. The last node in a linked list is going to, in C++ anyway, point to this in a non-circular linked list. We'll get to circular ones in a bit. In a regular linked list, the last node is going to point to null, and that's how we're going to tell we've made it to the end of the list. Okay? It's going to point to this value null. Null actually means 0 in C++ speak, but you can call it uppercase N-U-L-L, all uppercase, right? And you can check and see if a node is null. Here's the problem with, and we saw some of this on homework 1, or actually even more so in last week's lab. If you try to do anything with null, like if you said something like node dot next, and node happened to be null, do you know what happens? Yeah, it segfaults, it crashes, right? So you have to explicitly check for this thing. Supposedly the guy who made up the idea of null has like apologized for it. Because he said there are much better ways of handling the end of something than saying just point off into nowhere land, and or to the specific value, which is just going to crash your program. So he's apologized for it, and he calls it his billion-dollar mistake, because lots of people have like written programs that crashed and caused companies lots of money because of this exact issue. Yeah.
Does null equal to pointers, or can you also use null to assign other type of variables?
In general, null should only be used for a pointer. Yeah, there are other cases where you might want to use null for other things, but in general, only pointers. Yeah, let's stick to that for now. If you want to set something to 0, don't set it to null. Just actually call it 0, right? Something else, like a variable or something.
What if it's like a type that you created and you make it empty?
If you want to, right? If you have a type that you created and you want to make it empty, the only time you can set it equal to null is if it happens to be the pointer to that type. Because if you don't remember that, what will happen is you'll leak memory all over the place. Like and hopefully the compiler won't let you do that for a type that's not a pointer. Generally, it's pretty good about that, but that doesn't mean you can't forget this stuff. All right. other things on that. Okay, head, tail. The tail node is going to point to null. The tail is not null. The tail node has a next pointer, which is null. And that's that. Okay. All right. Here's the way we are going to start out by defining a linked list. Okay? You can do it with a struct. A struct is very, very similar to a class. In fact, under the covers, they're like pretty much the same thing, except that structs, everything's public by default, and classes, everything's private by default. Otherwise, they're really identical. We're going to stick to some fairly low level or fairly easy to understand structs in this case. In this case, the struct, it's going to have some, I said this very generically. I said some type, and we're calling that, and that's variable name is going to be data. That can be anything. It can be integers, it can be another struct, it can be a class. It's whatever your data is. Okay, that's what the type is up here. Okay, the node also has, this is kind of weird, it's got a node pointer to next. So it's very self-referential in that case, right? It says, here's some data, and then the next thing is the next node. And that's all there is to it, right? But that's the self-referential part of this. Okay, you have to actually, when you build a programming language, you have to think about things like this. Like if I'm defining a node, how do I refer to it when I just defined it? It's a little tricky, actually. If you get into language design, you'll see that. Okay. All right, self-referential node. Okay. What's cool about having this whole data structure is because you've got a very defined self-referential node that points to the next one, you can traverse, or what we sometimes call walk the list. Okay, in other words, you can go to the first node, and you can say, is this the one I'm looking for? Let's say you're looking for something. Is this the one I'm looking for? No. Well, go to its next, and then you'll get another node, and you'll do the exact same thing over again, right? We do this with a while loop almost always, right? You can't really do it with a for loop. Well, you could, but that would mean keeping explicit track of all the nodes, and you can do that. But it's so much it's a much better pattern using a while loop. Because all you do is you say, okay, while I haven't reached the place I want to go to, I'll show you in a second, right? While I haven't reached there yet, go to the next one, go to the next one, go to the next one, in this nice little while loop, and it takes care of your issues. Okay? And then when do we stop going through that while loop? If we haven't found our stuff? When it reaches null. So you have to do that explicit check. Okay? You'll see what that means. Here it is exactly. For to traverse this linked list, okay, this is what it looks like. In this case, I'm saying I'm just calling another node. I'm creating another node pointer called current. And it's a node pointer because it has that little star on there. Okay? And I am setting it equal to that head, which I said pointed to the first node. And then I'm going through and checking. And it looks easy on this one because it's a nice simple little while loop. But remember, there's corner cases here, right? If you happen to be at the head, or if you happen to be at the tail, or if there are these corner cases that you have to deal with. But in this case, while current is not equal to null, do some test on that to whatever you're testing. If you're trying to find a specific node, if you're trying to find out if the node's name is Harold, right? You're going to do that test in here, right? And then sometimes we do a break saying, hey, we've got it. And then when we do that break, our current will be equal to the one we're looking for. It's one way to do it. All right. You can also put a little bracket in here, and that light is going to be really annoying. You can put a bracket in here and do the actual stuff inside that block if you want to, right? If you want to do, and I'll show you an example of that too. Do some test inside that. If you have reached the node you're trying to reach, then you do the work inside that loop. Yeah.
So that break will just stop the loop.
Yeah. Good question. Break says, I'm done with this loop. Whatever the state is, get out and go down to here. That's what break does. Okay. Some people hate using break because it it tends to disrupt the flow of your thinking. I don't mind it. I mean, it's nice to use break so you don't have to go through the whole list until you reach null, right? Yeah?
You use break to exit the loop as soon as you found what you're
Yes.
looking for.
You,
Wouldn't it do that anyway if the test is true?
no, because it keeps going. Because what's happening here? We're just saying current is going to be the. In fact, this is the key line right here. Current equals current arrow next, meaning set my current to what my next of my current is, right? All right, and that would just keep going on forever. So otherwise, it would not do that. Now, yeah, I mean, you could. There's other ways of kind of getting out of loop, but that's the easiest way is to use a break in that case. Question back here?
Well, yeah, I was just gonna say then, couldn't you just have like two conditions to be met for the while loop? So like while the test fails, keep going in a way. So
You could, sure, you could. Yeah, you could have two things. I mean, the other thing you'd probably have to need an else statement in here so you don't do this again, right? So you could. There are other ways about it, but when you're programming, try to make things as simple as possible, right? And in this case, this is a pretty simple idea here. My test now passes. Get out of this loop. That's a pretty simple one right there. Yeah. You had a question?
So just like with the syntax of the if statement, do we need brackets or?
You mean here?
Yes.
You do not need a bracket there if it's a one-liner.
Okay, got it.
I probably should have done this in the interest of like space. You could put a bracket here and then a bracket after the break, and that would work. Ben, you have a question? Then Alex.
I was writing. I think I missed what you said about test on. What is test on?
So this is basically this is a very generic statement. I'm just kind of showing you the outline of this. This is saying, okay, so let's say I'm looking for some node that happens to have a name Barnaby, right? Right? Then, well, I would do a test here. If current dot data dot name equals Barnaby, then do this, then break out of this loop because I've found the one I'm looking for. That's all this is. This is just saying you're going to perform some test on it because you want to know if you found that thing, or you're going to do something else. I mean, if every loop is,
So that's an instruction rather than a code.
right? No, yeah, this is like pseudocode right there. That's not code, right? Yeah, sorry. Question, Alex.
Yeah, the pointer thing in the last line with the little arrowhead, is there another way to write that? Because I keep forgetting what that arrow is.
Is there another way to write this? No. If you've got a pointer, you refer to the pointer's elements with the arrow. And it looks like a little pointer, doesn't it? I mean, isn't that kind of nice? Like it points, right? Dash, right? That's how you remember it. That's how you refer to things that are getting pointed that are pointers, right? Can you use a star?
You reference it and then access next. So like.
All right, I guess you probably could. So you could say star current. Yeah, I guess you're right. Period next, like that. Yeah, you could. Sorry, that is the other way of doing it. This just looks hokey to me. I mean, you can do it, but I would rather you learn how to do it this way. Yeah, they actually do mean exactly the same thing. Good call. Okay, was that what all the hands were? Telling me I was wrong? Okay. Thanks. All right. Anyway, this loop will continue until either you find this test works or you end up with the current being equal to null. When you get out of this loop, the first thing you better check for is if current is really equal to null, because then you know you didn't find what you were looking for, right? Okay, you better make that choice. Yes. Just kidding. Just kidding. No worries, Maggie. Okay. A lot of people will go write this and then forget this part. And you'll go, my code's broken. It never actually does. It like just hangs. Of course it hangs, right? You're not actually setting the current to point to the next one. It's got to jump to the next node as you go along. Okay? Don't forget to do that. All right? I will see lots of that where you'll have to stop your program. Okay? It just hangs. All right. So let's see. Slide 12. There's a lot of text on this one. If we're going to remove a node we're looking for, we need to keep a pointer to the previous node. Why is that the case? So you don't lose what? Yeah, so let me draw this up here. And this is one of the cases where drawing this is an important skill to have, right? I think I may draw it on the next one. But in this case, if we want to remove, and this is true for the singly linked list as it turns out. Okay, I have 3 nodes here. And this one is, let's say this is node 0, node 1, and node 2. And if I want to remove node 1, this one, the one that's the second node, all right, starting from 0. If I want to remove this one, all right, I want it to be gone from the list. What has to change? Like, what pointers do we need to update? Yeah. So. Yeah, so if I leave that in here and say we're going to get rid of node 1 here, it's going to be gone. You have to change the pointers, the node previous to the one you're removing. You have to change its next to 0.2 and 2. Okay, that's how we skip it. So if we don't keep track of the previous one, you can't just say, oh, delete this one. Because you got to, how do you go backwards in a linked list? A singly linked list? You don't. You go back to the head and start walking it down again and call yourself silly, right? Because you don't want to like lose track of things. So many times we'll have this kind of method, right? We'll say, all right, our current is our head. Our previous isn't anything yet, right? Because it's the head. There is no previous node to a head. And then same thing, we're going to keep checking our current being equal to null. If we get to that current, we're going to do the deleting somewhere else, okay? But now we're going to say previous is current because it's going to be we're switching. We're saying, oh, now we're going to move current to our own next. So previous is going to be what we are now. Does everybody get that methodology? You've got, if you're keeping track of, here, we'll do it this way. Let's say we are walking down this linked list here, okay? And when we start out with previous equals null, right? The head points to our first node. And now we're going to say that current equals the head, so it also points to that first node. Everybody get where we start here? How this works out? Previous is nothing right now because we're here. This is the current one, and it happens to be the head. Okay. And let's say we don't ever get to the end. We'll just keep going down the end here. While current is not equal to null. Okay. So far, current is not pointing to null. So we're going to do this test. It's going to fail. Previous equals current. So what's previous now going to point to? Previous is now going to point here. And then we say current equals current next. Current, which is also pointing here, is going to equal current's next. So where's current going to now point? Whoops, wrong one there. Current is now going to point to this one. See how that works? Let's go through the loop one more time. While current is not equal to null, current, is it equal to null? No. So the test fails, let's say. Previous equals current. So previous is going to point to whatever current is pointing to, meaning it's going to change here, here. Current equals current next. So current is going to now point to what this one's next is. That's here. And now we're good to go. One more time through, right? We would say same thing. Previous would now point to this one because it's what current now points to. Current is now going to be equal to current next, which is null. So we can actually just say, look, it's going to point to null. Right? And then we would now fail our while loop here because current is now equal to null. See how that works, how you walk through the list? It's tricky the first time you see it. The 10th time you see it, it's OK. But notice, much easier to understand if you're always drawing this out or getting some sort of mental map of where the pointers are that you're trying to change. OK? Anybody have any questions on that? OK. All right. That's how you're going to go through this if you want to keep the previous one so that you can delete the one or do something with it. Okay? A lot of times you have to do that, and it's kind of painful. What I don't want to see is something like while prev is not equal to null, or something up here about prev. If you ever find yourself doing the following, like node next, next, right? You can do that, right? Because is this a node? Yes. Is next a node? Sure. Does the next node have a next? Sure, you could do that. The problem is it's going to get really ugly really fast, because if you don't do enough checks in here, if this one's null, right? If it happened to be pointing to null, there is no next. So it could get ugly there. So watch yourself. If you ever find yourself doing that, there is a case where, I'll show it to you in a few minutes. Sometimes you node, next, prev. Nodes that have pointers pointing back to the previous one, you have to do something like that's like the one case where you do that. We'll get to that in a minute. Don't worry about that right now. Okay? It gets a little bit hokey in a few minutes. Okay? We'll see how that works in a minute. All right, any questions about walking through the list with carrying the previous pointer along? Okay. All right. Whew. Oh, this is getting kind of a little bit extra code, right? I actually have to move the board down a bit because there's a lot of code here going on. In order to actually get rid of these linked lists, you update all the pointers that are necessary, right? Including the previous node's next pointer and possibly the head or the tail. If you are at the head or the tail, that's the corner case that I keep talking about, right? Okay. By the way, I forgot to mention this earlier. Side note. Some of the TAs were telling me that some of you guys were testing all of your homeworks. The only way you were testing your homeworks was doing make provide, right? Not a good way to test the homeworks, because we'll run some other tests on them, and it doesn't mean that you've done all the testing necessary. This is like a kind of a test here that you might want to you might want to write the test to see if this is working right. The idea is all these corner cases in here. Now, I wrote this in a couple minutes. There might actually be some bugs in here. I haven't actually run this through, right? But let's go through and see what's happening here. Okay, in this case, we're going to say remove node, and we're given some node that we want to remove. Can we automatically, in a linked list, go to that node and remove it? No. You can't, because the only thing you have is the head and possibly the tail. And if those are the only two things you have, there's no way to get to some node in the middle except by walking through the list. Okay, this is, again, why this is not the best thing in the world. Okay? Hey, Becky, if you're writing all this down, this is online. So it's probably not the best idea to write all the code down, but if you want to, you can. So now, let's see what's happening here. This is exactly what we did before, right? We're saying, oh, I'm removing a node. I'd better save the previous. I'd better walk through. This is the part where I was talking about, where you can either do this break or you can update. This time I did put the little brackets in there, right? If the current equals the node we're looking for, right, then we're going to go do our stuff. Yes?
In this case, do you also have to pass a pointer to head? Or is
depending on, so in this case, I would have this in a class that actually has a head based on the class. This is like a linked list class, and it's already got a head there. But yeah, sometimes you'll be writing remove node where you need to pass the node and the head. In this case, it's going to be part of the class. So good question. Yeah, good question. All right, so we're walking through this. When we get to the one we want, we actually break. Otherwise, we do this updating we just talked about. Okay? Half the page is just doing that, like walking through the list. Now, first things first. If the current is not equal to null, then we know we found the node we're looking for. Okay? Found the node we're looking for. If it's not, we didn't find it, we can't delete it. So this whole block here is only if the current one is actually a node that we're trying to find. Okay? So far, so good? Then look what I do here. If previous equals null, where does that mean we have to be? At the head. Okay? Because if previous is null, that's what we started out and we said, look, previous starts out at null. If we never changed it, it would still be null. There's really no other way it could be anything but null, or no other way it could be null, except in this case where we're at the head. So therefore, now what we say is head is now current next. Right? Okay? And now we've bypassed that link. Now this is another case where drawing this out is not a bad idea. If we're at the head, right? If we're at the head and previous still points at null, right? And current, right, points to the head there like that. Okay? By doing this statement, head equals current next, we're saying the head, instead of pointing to this one, is now going to be pointing to what current points at also happens to be the head, next. There. And have we bypassed this? Or bypassed this, I should say. We bypassed this. All we need to do now is make sure we clean up after ourselves and delete this one. Okay, so that's how we're going to do this. We also, some of you might be raising your hand and say, couldn't you say head equals head next? Yes, you could. Was that your question? No, what was your question?
So in that case, then, if it was one of the double linked lists you just said.
Yeah, don't worry about the double linked list quite yet, but yes, you would have to do some more pointer changing. Okay, you would have to do some more pointer changing in that case. All right, let's see, what else about this? So we've changed the head. We're going to now delete current at the end here. Otherwise, look what we have to change. We have to say previous next equals current next, and that's bypassing this. So if instead of being the head here, this was another node, we would say previous now points here. The node we're trying to delete points here to the second node. We are trying to say previous next, this pointer here, goes to current next. And then we bypassed the one that we're trying to delete. Gotta draw, and this is actually a terrible drawing. Sorry, let me just redo that real quick here. If you have 3 nodes, all right, like that, and we're trying to get rid of the one in the middle, right? That means that we found this one, which means current. Current should be pointing at the one we're trying to find. We found. Previous points to the one right before it. And what we're going to say is previous next has to change to go over the link that we just deleted, meaning it has to be previous next has to equal current next. And that means that it will now go to there, and now we have successfully bypassed this. Good? And then we delete it. Yeah?
So we delete current before we do everything else, and then instead of assigning head to current next, we assign it to head next, and then on the second line, we assign prev next to prev next, next, next. I know you say not to do it, but we know that it's not going to be null. Would it still work?
So, okay, so you just said a lot of stuff that might work. Do it the easy way. Like, don't try to overthink it, right? You're right. I mean, if you try to delete the currents right after you found it, hey, maybe you could, right? But then you've somehow lost information that you don't want to have to do, right? Okay, in fact, you couldn't do that, as it turns out, because the minute you delete the current, this pointer is no longer good. So it's next. The pointer from current's next is no longer good. So you can't even delete current until you've already reassigned, until you've used that next one too. So you've got to be really careful. So maybe it would have worked, probably not in that case. Don't overthink it. Yeah?
If say this were like a list of integers or whatever,
Yep.
you deleted one of those nodes,
Yes.
does that free up a place in memory for like if you were to add a list or to go there and it would just point to this place?
Not necessarily. Yeah, integers are an interesting case because generally we don't use the new keyword for integers. So in that case, yeah, I mean it wouldn't automatically use that for the next one. No, not at all. Like,
is that how you get fragmented?
yeah, that's how you get fragmented things. Yeah, yeah, you want to kind of avoid that. But if you follow this method and you do deletes where you need to, it should be fine. And if you don't, it's not going to matter if you didn't use new to make something, you don't need to worry about using delete on it. The memory system will handle that at some point. Okay? Yeah. Other questions? No? Okay. All right. Update all previous or all pertinent pointers. Drawing the situation is important. And if you're like messy like me, draw it again. Right? In this case, this is insert node after. All right, insert node after node 1 and new node. This is the way I'm saying this. I should have defined this better. Insert node 1, insert after node 1, and what we're inserting is new node. Okay, everybody get what's going on here? So in here, we're going to try to put a new node. We're going to put a new node in here. That's where we're going to end up doing it. Make sense? All right. Can I automatically go to node 1? No, you got to walk down the list to get there. Okay, so we're going to have to do that. This is the new node we're going to put in here. If you draw this on the board, actually I actually have it here. Look. New node 1's next is going to point to the new node, and new node's next is going to point to what node 1's next was. Okay, it's a little hard to see on two slides, like over across two slides. But basically, you're saying change this pointer and change this pointer. And this one needs to go here, and this one needs to come back and go there. And you have to do that in the right order. Otherwise, you'll lose this one. Okay, remember, this is all about bookkeeping in this case. All right, that's what we're going to draw, and that's what we're going to try to do. We're going to say node 1's next goes to new node. New node's next is going to what was being pointed at by node 1's next. Yeah?
So when you declare new node, was its next originally pointing to null, or just like some that's correct?
Who knows? All you care about is that it doesn't matter what the next of new node is pointing to at this point. Because we're just inserting it in there. And if it was pointing to something else, different story. Now, what we're not doing is we're saying insert this linked list into another linked list. Totally different idea. Then you would have to walk all the way down to the end of that first linked list and then figure out which pointers to do. But yeah, that's that. Yeah.
You probably said it before, but is node 1 a pointer to a node, or is it the node itself?
Well, it's a good question. Node 1 is a node. Like, this is somewhere in memory, right? Up here, this is definitely a pointer to, up here, this is a pointer to node 1. Yeah, good question. Right. I should have put the definition of the, like, what that we're trying to do there. But those are both pointers. OK, here's what it looks like. OK, all pertinent pointers. We can't go straight to it. We have to walk the list. In this case, because we're inserting after, you don't need the previous one. It doesn't actually matter. So you just keep the new one. We're just going to look, and we are going to, let's see. Sorry, I forgot. This is where we're walking it. Up here, if we happen to be, this is like a corner case in this case. If there is no list yet, how do you insert after a node, right? And this is a weird case because in this case, you'd have to be passing null in here as well. So I threw this in to say, hey, look, you do have to think of some corner cases like what if the list doesn't even exist yet? In general, the list will exist. Today, before I post your homework, I'm going to try to make sure I answer a lot of these questions. But if you don't understand exactly the parameters, ask on Piazza and we will clear them up. OK? Now, here's where we do the walking through the list. In other words, setting the current equal to head. And then in this case, I only broke after I dealt with the node. So in this case, we say, OK, look. While current is not equal to null, if the current equals node we're looking for, this is where we have to change new node's next to be the node we're looking for is next. And then we change the node we're looking for is next to equal new node, and we have inserted it right in the middle. If this code doesn't make sense to you, go back to the picture and see exactly what we did. Because I drew this picture. I said we have to go from this, which is 3 nodes, inserting after node 1. I'm inserting it like this, meaning node 1's next has to change and new node's next has to change. And then go back and look at the details like that. Question?
If we're given the node in the linked list, why do we need to search through the list? Because aren't the things that we're concerned about so you have that original node.
Oh, yeah, good point, good point. In this case, let's see, do we need to actually look through the list? Actually, in this case, you're right, we wouldn't. This is probably another example where I should have said something about the node. You're right, yeah. So in this case, that's a very good point. I gave you the node itself, and in that case, sure, if you know it's a node in the list, then you would be able to go right to it and change it. Yeah, you wouldn't have to do the while loop. Good point, fair point. Okay. Normally, we'll give you something like insert after the guy named Charlie or something like that. Yeah, sometimes. But yeah, you're right. That's a very good point. I goofed on that one. Yeah. Okay. Anybody get what he was asking? Saying, look. Because I actually gave you the node, well, then you don't have to walk the whole list because I told you where it is. All right, fair enough. All right. Inserting at the beginning of a linked list is easy. Why is it so easy? Do you have to walk anything? No, you know where the head is. You're at the head. You do the insertion. You're done. No need to walk anywhere. And you do need to maybe check and see if there is no list yet. But all you need to do is say, look, new node next equals what head next is pointing to, and the head is now the new node. And we've now inserted into the beginning of that list. Kind of cool. What's the asymptotic behavior of inserting at the beginning of a list?
Linear?
it would be linear if we had to go all the way through the list, right? But in this case, I don't care if the list has 1 billion elements in it. All you have to do is go directly to the head, do this pointer exchange, and then that's it. So it's not linear in this case. It's what? I heard it over here somewhere. Constant, actually. As it turns out, it's constant because you don't care if there's 1 million elements in the list. You can just automatically go right ahead and do it. Okay? So it's order 1 in this case. We call that constant. Great. This is one of the benefits of using a linked list. If you want to insert at the beginning, it takes constant time. No need to worry about it. Remember, inserting at the beginning of an array is linear because then you have to move all the elements over. Move them all over if you need to keep them in order. Okay? All right. Inserting at the tail, on the other hand, you have to walk the entire list from the head if you didn't keep a tail pointer. And sometimes you don't. Right? Most linked lists actually don't have tail pointers. If you don't have a tail pointer and you want to insert at the tail, you have to look through all billion of them before you get there. And then you find the last one and then do the insertion. Okay? What's the asymptotic behavior of that? Inserting at the tail? Now it's linear. Yeah, now it's linear. Okay? So let's see. Now it's order and linear. If it has a tail, what's the asymptotic behavior? Constant again, because you just do it. You can go right there and do the exchange, right? Now, you have to know what the actual tail node is. You can't just say, oh, it's null, and I'm going to insert it. You have to know what the tail node is, right? Yeah, Ben.
Even if it has a tail, don't you still have to make the last one at the end of the list point to it?
You do. That's the tail. So the tail is the last one, and now it's going to now point to the new one you just inserted.
I mean the node leading up to that one.
Nope, you don't, because the tail is already the second. Now it's going to be the second to last one. So that one's already got something pointing to it. Make sense? Draw it out if you have trouble thinking it. Go, oh, okay, I see. I'm at the tail. I'm at the tail here. This is where I want to insert. All I need to do is add the new one right there. I don't need to change this pointer. Does that make sense? Yeah, I do need to change the tail to now point here, by the way.
And the one that's pointing to null, though, should point to it.
The one that's pointing to null should point to this.
Yes.
Right. This was the tail. Right? And so I can go to the tail, and I can insert after this one. So I know what the tail null is. It's not pointing. It's pointing null right now, but it needs to point to this one, which I can update immediately. And then now I need to point the tail to there. Yes, those are the two steps. Yep. But you see how you didn't have to know the one before the tail? Look it over again. You didn't have to go through. If you have a tail pointer, you don't have to go through the whole list. So here's a tip. If you think you're going to be inserting at the beginning of an end and an end of your linked list, build a tail pointer in and just make sure you update it when you need to. More bookkeeping, but you have to update it. Okay? All right. Searching a linked list. So we've already done that. Right? We've just walked through the list to search for whatever we're trying to find. Okay? What's the behavior of searching a linked list in the worst case? Linear. You have to go where? All the way to the end. Right? That's the worst case. What's the best case? Constant. It's the first one. Right? That's the best case. For arrays, we can order our data such that we can do a binary search in an array and change it from linear behavior to logarithmic behavior, which is great. Is there a way to do that in a linked list? Can you think of a way for a linked list to do some sort of binary search? If you make a tree is not a linked list. It is a tree. A tree is a linked structure, but not a linked list. Good question though. Jean-Marie. If you start at the head and the tail, it doesn't even cut it in half though, really. I mean, you still have to go. Let's say you're in the middle somewhere. I don't care if you go there from the back or the front. You're still going to take the middle amount of time. Now, you could say I'm going to guess and say that it's from the tail, and then sometimes you'll do better than order n divided by 2. But we're not even going to worry about those weird cases. Yeah. You could create an index. How are you going to store that index? In an array, yeah, exactly. So, good call, but yeah. No? Yeah.
You could insert them at a certain spot in the linked list based on something about the data, and then it's ordered.
Insert them at the linked list, but how do you find the one you're trying to, like, if I've got a linked list, right, and it's got 60 pointers here, right, and you say, okay, fine, I know they're in order. Awesome, right? Well, how do I get from this one to this one? There's no way to do that unless you go through this one, right? This pointer is only referenced by one guy, which is the previous pointer, previous node. Yeah, it's tricky. Yeah?
So we did this in a project Comp 11, which was that we used multiple linked lists.
Ah.
Like an array of linked lists, essentially, and you could use the array. So like say it's a database of words, you can get an array of A to Z.
Sure.
And you know if it starts with an A or it starts with an A.
Yeah, that's a great idea. That's not a linked list anymore. It's like a hybrid data structure. But yeah, that's a good way to do it. You can do that where you get extra information by building more data structure parts to it. Sure. Yeah.
So I mean, I don't know. This is gonna step out of the definition of a linked list. But I mean, could you not have a linked list that is a sub-linked list within it? So if you have like every third element has a pointer going, so you could.
Oh, sure. Yeah, you could do something like that where every third element points like to a head or something, and yeah, maybe you could. Maybe. I mean, yeah, that is definitely not a linked list anymore. That's some sort of hybrid. There's a thing called a skip list, which we'll learn at the end, which is kind of got these kind of ideas in it, where you're skipping ahead a number of things. Yeah, good ideas. The answer to this question is there a way? No. Really. Right? You can't do a binary search on a linked list by definition of a linked list. Okay? All right. What is the key issue when deleting a node in a singly linked list, even if we know where the pointer is to that node? We kind of went over this already. If we know where that node is, what's the problem with deleting it? Yeah?
You need to be able to point to the next.
You need which one?
That one that you're deleting.
You need the one you're deleting, and?
The next.
Not only the next, you've got the next, you need the previous, right? That's the issue, right? You can't simply delete a node, you have to find the previous one by going through the list, right? Can we avoid this? We can, if we have this thing called a doubly linked list, okay? A doubly linked list says, I'm going to point to the next, and I'm going to point to the previous, and it's lots more bookkeeping. Yeah, Maretta?
Other than like the bookkeeping wise, but for memory, is a doubly linked list way bigger than one list? Like, why would you ever have a linked list if you could always have a doubly linked list?
Normally, you don't have just a linked list. Most linked list implementations are doubly linked lists for exactly the reason. Pointers are small, so having one more per node is not so bad. Here's what it looks like. Okay? This is what it looks like, and it gets a little ugly here, but it says each node has a next and a previous, right? Each node has a next and a previous. There's still a head and a tail. The previous of the head points to null. The next of the tail still points to null. That's your linked list. This is what today's lab is about and tomorrow's lab is about, a doubly linked list. What's nice about this is if I say delete node n and I have that node, which is what we were trying to do with insert after, if I have the node, I go right there and I need to do some updating, right? This gets ugly. You have to draw this, right? In today's lab, you'll have to draw this if you want to do it. Look, if I'm trying to insert, right, after this node n, I have to make 4 pointer changes. Why? I have to change new nodes next to point to this node that new n is now pointing to. I have to change new nodes previous to point back to n. I need to change nodes, the n's next to point to new node. And I have to change n's nexts previous to point to new node as well. Whoa, that gets ugly. Okay? I've done it right here. This is not quite complete because there's some corner cases in there. I'll shift right ahead. I'm not going to make you read this right now. There's some corner cases in there if you are at the head or at the tail or what have you. But the idea is draw it, code it. And if you draw it and code it, you can annotate where you are with everything, okay? 2 last slides. There is a thing called a circular list. What does that mean? It means the last pointer's next, the tail's next, points all the way back to the head. What's good about that? Starting at any node, you can now walk the entire list without going back to the head. It's kind of nice. You have to be really careful. You have to keep track of where you are. because you will walk it forever if you don't. There is no nulls in that case. There are no nulls. Yeah.
Would you have a tail on that?
Yeah, you still call this the tail. But you're right. In general, no, there's no real tail in that case.
It could be the head, because technically...
It could be the head. Yeah, it could be any node, could be any other node. But you need to keep it pointing toward to one node at least. Okay. You can certainly have a singly linked circular list as well. Okay. I talked about the lab a little bit. If you have questions, ask them during lab or on Wednesday. Okay. See you guys later.